Thanks. So I was just telling you a little bit about CERN. So CERN is an international organization. As a lab, it was founded many years ago. You can see 1954. It's at the border between France and Switzerland. It's one of the biggest fundamental research facilities, and you will see why. It's dedicated mostly to particle physics, but we actually have a few more experiments that are going on at CERN. We have about 3,000, more than 3,000 staff, but we also get a lot of visiting scientists and associates that come to do their research at CERN. You can see here how many countries are actually participating in a way or another in the CERN scientific program. So CERN is famous for the Higgs boson. You also mentioned it before. This was one of the plots that showed it in a slightly more, in a simpler way. This is the way it appeared on the news. This was 2012, already a few years ago, and it was one of the most important discovery in recent years. Now, the Higgs boson was really the missing pieces in what we call the standard model of particle physics that describes all the way matter is done, and describe most of the known aspects of our universe. If you think about it, this just goes down to 5%, and so indeed there is more than 95% of the universe that is actually unknown. And the goal of experiments such as the ones that happen at CERN are really to try and understand what this 95%, what this huge fraction actually is. More, what is dark matter, for example? You might have heard of it. What is the difference between antimatter and matter in nature? Where it's originating from, and how gravity actually really works. Now, this happens at CERN through a very large facility. The main accelerator is the Large Hadron Collider. Is a 27-kilometer ring that is under the Swiss-French border. You can see Geneva Airport here. There are 4 main experiments that are analyzing collisions from the LHC. Those are the ATLAS and the CMS experiments. So ATLAS is where I worked for some years, and ALICE and LHCb are 2 others experiments targeted to more specific problems. In general, what makes it really challenging, I would say, is the fact that CERN is really a big data facility. The data that is produced goes up to a petabyte per second. So if you try to make some different figures, this would be about 2,000 disks per second. Not all this data can, of course, be analyzed. In addition, when we talk about data at the LHC, we talk about data produced by the experiment. So we talk about data that has some physical meaning, what we want to analyze in order to understand the questions I mentioned before. But also there is a lot of data that is produced by the infrastructure. So by the accelerators infrastructure, by the detectors infrastructure, and even by the computing infrastructure that we use to analyze the data. In particular, if you think about computing, for example, we have more than 170 data centers in the LHC computing grid that are spread across 40 countries. And this sums today up to almost 1 million CPU cores and about a exabyte of storage. Now, this is the situation today. What we know is that the next generation colliders will actually require much more, let's say, complex detectors, highly and will need to study problems at a much higher precision. And so there will be the need to actually devise techniques that will allow us to develop, to analyze a larger amount of data in order to extract more and more complex information. Now, for all let's say the whole data processing chain at CERN, we are now developing classical machine learning algorithms. And this is basically one of the reasons why we turned into investigating quantum machine learning algorithms. So this is what you'll see here today. A few months ago, we started at CERN the Quantum Technology Initiative. This goes beyond quantum computing. It's actually the idea beyond this is really to try and investigate the quantum technologies more in general, anything that has to do with sensing, for example, and direct applications to the experiments, either collider experiment or others, as I mentioned before, targeted to understanding cosmology or astroparticle problems. And quantum communications, so encryption, distribution of quantum keys. We have, for example, an open QKD node that is installed in the CERN data center. As far as theory is concerned, quantum technologies could really improve the way we do perturbative QCD, we simulate lattice QCD or other problems our theorists colleague work with every day. Now, computing is if you want, is something that goes that covers all the topics I mentioned before. It's connected to all of them. It is some sort of backbone to all those kind of initiatives. There is the aspect of algorithms. This is very important. CERN as a physics lab has a lot of experience in anything that has to do with quantum field theory, for example, from a theoretical perspective, or with analyzing data that is originating from quantum models. But what we need to do at this point is try and understand what parts of our data processing chain could profit from a quantum approach in computing. And so this also means building expertise as far as software stacks are concerned, as far as simulators are concerned, and provide the infrastructure that will allow our researchers to actually do their research in this field. And then there is, of course, all the discussion about what you also mentioned before. So the importance of collaboration. For us at CERN, cooperation and working together with other institutes and with industry is a priority. The idea of community building and knowledge sharing are really at the core of development of any R&D, right, or of any progress in science and research. So, more specifically, why quantum computing in high energy physics? Now, the idea is that the data is generated by quantum processes, but the data we read out of our detectors is something that we measure. So that is classical data. The hypothesis is that quantum correlations that happen between the particles can be probed by studying those measured quantities. For example, angular correlations between the momenta of the particle. And in such a way, so doing those kind of measurements and analyzing this kind of classical data, we can get back to understanding the laws of quantum field theory, the quantum core underneath. Now, we can do that in classical ways. As I said, we are developing deep learning models to do that. They work very well. But we can also wonder what quantum computing could do with respect to this problem. It could be that quantum algorithms would be could naturally deduce those kind of quantum correlations even from classical data. So if you want, this is the generic idea why we are looking into this problem. Now, quantum machine learning. There is, of course, more to say about quantum machine learning in terms of why we are looking into this into this specific approach. As far as quantum algorithms are concerned, I think there are many reasons. One of the reasons is that, of course, you can use machine learning and deep learning, whatever, to solve many different problems. So in some sense, if you manage to prove that quantum can actually accelerate machine learning, then you might be able to solve a lot of different problems in one with one stone, right? So this makes it very interesting. There are also other reasons related to the fact that it might be more suitable for near-term devices. I don't want to go there. It's also very difficult, I think, for this kind of algorithms to define advantage. In our case, as in most, let's say, applied studies, what you really want to check is and understand if what you can get is a sort of runtime speed up. Although this, again, it's something that's difficult to define for quantum machine learning. Do we want to are we talking about time to convergence? Are we talking about pure computational complexity? Then there is everything that has to do with sample complexity, of course. Can we train our model with smaller samples? This is something that would be very useful for some of our applications, for example. And what about representational power? This connects what I mentioned before. So it could be we could be able to understand quantum correlation beyond the current performance of classical models. So those are all, let's say, questions that we try. It's not really question, let's say, points that we would like to understand better. Then there is all the discussion about practical aspects, the practical side of all of this. So, of course, we all know that the situation of quantum hardware today is not ideal. So we need to be able to run and to adapt our algorithms in order to, take the best, the most out of the current hardware. And then there is everything that has to do with, the size of your problem. Many very nice examples and tests and studies are done on toy examples. So how far are we to actually, being able to solve a realistic problem? What does it mean? What steps do we need to take in order to get there? So those also are very, very important, because as I mentioned before, this is really a applied sort of investigation. So our strategy for now has been, for the past couple of years, has been to really try and identify some specific use cases in our data processing chain that we could control very well, that basically we know how to solve classically, and to try and understand how, what does it mean to actually re-implement this kind of, not re-implement, but to try to solve this kind of problem with a quantum algorithm. So you see some examples here. This is all, I list a few collaborators here, and this is not an exhaustive list, I believe. Well, yes, if I do that, you can see that we chose different specific, high energy physics use cases that in any case are representative of more generic problems. So when we studied, for example, quantum support vector machines for Higgs boson classification, this is, it's an example of a more generic classification problem. We wrote quantum tree tensor networks to do particle trajectory reconstruction as an example of pattern recognition. We are studying quantum generative adversarial networks for detector simulation, but generative models are a very, large and versatile class of models that can be used for very, very many different applications. Another nice project we have is about quantum Boltzmann machines. We are using those to set up a reinforcement learning framework that we're using to optimize the configuration of our particle beams in the accelerators. This is also, I don't have results of this, unfortunately, not yet. Need to wait a few more weeks. This connects to what I mentioned before, our idea of trying to understand how we can make the problem as realistic as possible. So studying hybrid data embedding in order to extract the most possible information from our classical data and optimize it for the quantum algorithms. So let me give you some examples. The generative models are one of those categories that we've been studying for longer at the classical level. We've been using GANs or variational autoencoders, but primarily GANs, so generative adversarial networks, to replace Monte Carlo. The problem, as in almost all scientific fields, is that Monte Carlo can be very, very precise, but unfortunately it's also a technique that is very expensive in terms of computing resources. So it's been a few years now that we've been studying deep learning to do this, to replace it. And GAN, in spite of their, let's say, being notoriously difficult to train, can provide very precise results. So the example that you see here is a hybrid quantum, classical quantum GAN that we apply to the simulation of a specific detector that can measure the energy of particles. Now, the initial test we did used a model that was developed by IBM, originally by IBM, and it was meant to load the probability distribution in quantum states. So the idea of that model was really kind of different than the real generative application, but it focused more on a way to try and load in a quantum circuit information extracted from the training data set. In any case, we started with this. It looked like a relatively simple model, and we optimized it for our use case. And you can see some examples here of using 3 qubits to represent a one-dimensional energy distribution. So you can imagine a particle that enters the detector in this direction. This represents the detector layers, so depth. And the histogram is just showing you how much energy is deposited in the detector. If you use 6 qubits, then you're able to generate 2-dimensional images. You can see a comparison here between the real image and the one generated by our GAN. And this was, as I mentioned, this was a relatively simple example that we built as a variational circuit using just 3 layers of Y rotation. We went beyond this and started a project with Cambridge Quantum Computing. Now, I mentioned before the original model, IBM model, was meant to learn some average distribution, but what we really needed was a way, or is a way, to generate samples, so to generate images of particles going through our detectors. So we decided to build on that model, modify it, make it more complex, and we built an architecture in which we use 2 generators, or better, a 2-steps generator, quantum, that learns the average distribution and then samples images from it. This is still based on Y rotation variational form. I also list here the classical discriminator that is used in the adversarial training. And you can see that it actually works very well. We can reproduce the mean image, the average image. Again, this is the comparison between the expected value, so the real original value in red, and the GAN result. We can generate some patterns. So those would be, each one of those energy patterns would correspond to a different particle that went through the detector. And you can see that the training, well, okay, here we also report losses and relative entropy, that it's going down nicely. The problem with this model, actually, I don't mention it here explicitly, but this still requires some work to do, is that the number of images that you can generate with this model is related to the number of qubits that you use. So this is really not something you want to keep, because it means that it becomes very, very difficult to scale. You will need a too large number of qubits in order to generate all the images that you need. So the next thing we tried was to move to a continuous variable architecture. So in this case, we decided to encode our input information into display states. This is work that is done using strawberry fields and penny lane, of course. And in this case, we did actually different tests. So of course, the easiest test we could do was to again build a hybrid model. Again, a variational approach. In this case, we set up a generator with 8 layers, and we train it against a classical discriminator with fully connected layers. You can see the results here. Basically, let me explain to you. This is always the same data sets that we just downsample or upsample, depending on the dimension, the number of qubits that we want to use in the example. In this case, we use 3 Q modes, and you can see that then, therefore, those kind of images represent always the same thing. So this would be the detector depth, and this would be the energy that is deposited by each of the particles that go through. So you can see the typical, these are real images. You can see the typical behavior in which the maximum of the energy depositions happens in the middle, but then also you have cases in which actually most of the energy is deposited at the end. So you see those lines that peak down here. So we trained our hybrid GAN, and we managed to get a nice representation of the images. You see here a comparison of the average image, and also you can more or less have an idea of how real images look like. What was interesting for us was a direct comparison to a classical GAN that we designed to solve the same problem using purely fully connected layers, and see the results. Basically, what we saw is that in spite of the much smaller number of parameters in the quantum generator with respect to the classical generator, the hybrid model was able to reach convergence in just about order 100 epochs instead of order 1,000. So this was a very, very interesting result for us. We are now trying to move away from a hybrid model. So we started studying the performance of a quantum discriminator. So basically just a classifier that would be able to test if we just if by defining the discriminator as a quantum circuit, we could indeed keep identifying correctly the particle energy profiles. And you can see some tests here that are run using different backends, the Gaussian and the Fock backends. We don't see very big difference at this stage between the two. Maybe the Fock seems to be slightly faster in convergence with respect to the Gaussian. But if you go and look at the prediction, so the confusion matrices for the two cases, they pretty much agree. They're very close to each other. So we were happy with our quantum discriminator, and we built our fully quantum GAN model. Now, in this case, basically, the difference would be not to have any measurement between the generator and the discriminator. Unfortunately, we observed the mode collapse. I mean, what are the chances, right, using GANs? So our first test with the fully quantum GAN yield something similar to a convergent, but clearly collapsing. You can see very well that only some models, some very few energy patterns are generated. So this is something we're still working on. Let me check the time. Yes, I'll take just 5 more minutes to show you 2 more examples. I mentioned before the problem of reconstructing particle trajectory. So reconstructing particle trajectories can be very complex mostly because of the dimensionality of the problem, the occupancy, the number of signals of hits that we expect in our detectors in a realistic setup, of course. So classically, we are developing graph neural networks in order to do this. The idea is that you can model your problem as a graph of connected hits, and then use geometrical constraints to optimize the trajectories. The problem, again, from the classical perspective, is that this yields very, very large graphs. So we tried to see what would happen in trying and in using quantum networks instead of classical networks to do this. Of course, with smaller examples, okay, in which we reduce to about 1,000 the number of total hits of total particles that we are studying. You can see the results here. So there are 3 different kind of hierarchical classifiers that are used. In general, so 3-tensor networks and merographs seem to work slightly better, and this is the area under curve, and this is the number of parameters that is that build up the networks, basically, and they are compared to the classical models that, again, we have simplified for the sake of this of this comparison. So you can see that when we reduce to similar number of parameters, then the quantum classifiers and the classical networks can yield similar performances. This is not the case. When you increase the number of parameters, the classical of course gets better. The last example is a classifier. So everything you've seen up to now has been built as a variational with a variational approach. For this Higgs classification problem, what was used instead was a kernel approach. So a quantum SVM was trained in order to identify Higgs events from their background. This is very important. You can see here an example of how, the result of such an analysis. This is the result actually of the classical analysis that uses BDT, by the way. So what you need to do once you measure your data, which is this black points distribution, what you need to know is how much of that data is coming from a signal and so from the Higgs, and how much instead is just background that is basically different particles that generate the same kind of generating the same kind of signature. So you can see here the results of this quantum SVM that was trained on only 10 input features. Basically, a principal component analysis was used to reduce the number of features from the original, the set that's used in the classical case, to what we encode in the quantum circuit. The results are here. In one case, you see here the area under curve, and this compares the classical SVM, a BDT, and the quantum SVM. If you take into account error bars, I would say that the performance are similar between the three methods. And on this other plot is instead showing the ROC curve for obtained on the simulators and on the real hardware. This was This was run on the IBM Paris with about, I think it was 27 qubits or something like that, around 20. So let me conclude. What I wanted to stress with this talk is really there is work that we are still doing in trying to understand, characterize better how quantum machine learning models work. Everything that has to do with training them. What does it mean to properly design a model in a quantum circuit? What does it mean to try and reach convergence? And at the same time, what is their representational power? How could they be used to improve or to solve specific problems in the ion energy physics domain? And of course, this comes with a lot of additional investigations. This is all part of a more generic, set of efforts that CERN has started in order to understand quantum computing and understand how it interacts with other fields. And again, I would like to stress that this is really something that it's a field that can really profit from a strong collaboration between scientists and between industry. And that's it. Thanks.
Thank you so much for Sofia. That was fantastic. Wonderful talk. Lots of interesting questions coming out of the chat. Before we get to those, I want to ask a sort of maybe a high level question first. This is a very naive question, of course, but so when we think of the successes of deep learning, we've seen that deep learning is really successful in cases where we don't really have a model. So, for example, recognizing images or in an NLP where we can't write down the rules. But with physics, it's all about rules. We have very good models. So how is it that deep learning can work well with physics? Where's this?
It's actually a very nice it's a very nice question. It actually is also something that I think it's particularly interesting for me. I remember when I started to work in deep learning in physics, my approach was really okay. Let's leverage the ability of deep models to understand features that we don't know about. Okay, so let's use them to skip any possible bias that human knowledge could bring in, right, when you start your data analysis that way. Now that worked very well, and I was actually surprised of how well this would work also for our use cases. But up to a certain point, beyond that, we realized again that indeed introducing what's called domain knowledge, so introducing what we already know of the physics that's underlying the data that we want to study, that can really help you get, cover the last few percent of accuracy that you really need, because you need to get to that sensitivity. So I would say that we are back at the not back. We are at the point in which there is a lot of research now in trying to properly introduce physics knowledge into deep learning and create physics aware models, basically.
Okay, that's very cool. I could definitely go to do some more research on that myself. So it's something I'm very interested in. So lots of great questions coming from the chat. I will now I'll let them have their turn. So we got Q_Severgus asking, how far away are we from having QML in high energy physics, and if the limiting factor is infrastructure?
Many questions in one. So how far are we? We are here. We are where I showed you. These are prototypes. Those are examples. Those are models that we are developing for simplified problems, realistic, but in terms of dimensions, they are simplified. So we are still far away. I mean, in a few years' time, there will be the new LHC round that will start. So they are called the high luminosity LHC. So there will be a big splash in terms of needs for computing resources. We will not get those models ready by then. But the research is needed. It's needed now because again, it's a change of paradigm that is needed in order to make those models work for real use cases. So I would say that the limitations, the limitations are different. If we are talking about deploying models today on today's hardware, then of course we need to face everything that has to do with the coherence problem, with noise, with the number of qubits that we have access to and their topology. So we need to adjust our model, limit our model in order to, so that they make sense in this kind of environment. In an ideal case, of course, no. Then we could think of designing circuits that could analyze also even huge amounts of data. If we could leverage entirely, the exponential advantage that you get just by using qubits instead of classical bits to represent your data, that would solve a lot of problems. But unfortunately, we know that is not just it's not straightforward. So limitations are resources in some sense, but it's also a matter of designing. We are still at the stage of correctly designing algorithms to solve our problems.
Cool. Maybe another question in this interesting overview area. I'm curious to hear an answer to this one myself as well. Do you have? So this is actually from Maria Schuld. Asking, do you have more examples of where one could do QML directly on particles or fields of interest, i.e. on quantum data?
So we have, it's what I mentioned here. So the examples that I show in some cases, like this example, this is a case in which we are trying to use the quantum algorithm to speed up a pure data processing step, right? So we are trying to improve the way we reconstruct particles. So maybe it's not. So I like this analysis very much. I contributed to that. This is not. I'm not. I don't want to diminish its value in any way. But what I mean to say is maybe this is not the easiest place to go and see advantage coming from quantum. If we are instead looking at generative models and where we are trying to reproduce, so classical generative models have their limitations in terms of representation of power. If we are trying to use them to reproduce, to learn properly quantum processes and use them to generate them, then this could be an example of direct QML application that could show advantage. Now, of course, the problem here is to train them properly, I would say. And then there's everything I mentioned here before. So where is the plot? Yeah, here. So whenever we are really trying to analyze specific channels, so there are specific physics signatures in which the correlation between the underlying quantum event and what we can measure is stronger. And so it's, or let's say, yeah, it's more direct. And so here as well, again, even by analyzing measured data, so classical data, we could probably get an advantage by going quantum.
Okay, cool. So Dr. Felipe Freitas is asking, how much information are you allowed to lose in the process of encoding the input data to process in a QML model? You were talking about down, I think, at one point.
Wow, this is another good question, something we are trying to study now. I think it's very much case dependent, but I can give you an example. So if you go, I mean, if I show you here the SVM problem that was applied to Higgs. So in these cases, the initial classical analysis used 40 features. We use PCA now. PCA is an approach that is going to, properly model linear correlations, right? And in this case, we use it to reduce the data to 10, a set of 10. It seems to work very well, doesn't really make much difference we don't really see much difference between the classical case and the quantum SVM case when we use the same 10 variables. If you use more variables, so if you go back to the original 40 input features variables, then the situation is completely different. The classical model with the full set of information still works best. So the answer to the question is really like, what is the target? What is it that you want to achieve, right? If you can live with a problem in which a reduced amount of variable, and it's not, what I want to say is it's not just a matter of quantity of information, it's the quality of the information that it's important, right? You might want to use, in a case like this, an autoencoder, for example, or a hybrid autoencoder that maybe it's capable of capturing and keeping in its latent space a better set of information that then you can use in the classical, in the quantum circuit. But I don't have a definite answer to this yet.
No problem. That's what research is all about. So Adri Persa is asking, ML is commonly used at CERN to study the QCD background in the experiments. Is there any project related to this topic using QML?
Yeah, well, this is an example. There are a couple of more, for example, that we are working. They are mostly developed at Tokyo University, ICEP. They are still looking. They also looked into QML for reducing background. We have another project with ETH in Zurich, where we are studying variational quantum classifier versus quantum SVM to select a different kind of Higgs decay. It's different here. Here, the Higgs particle is selected by decaying into 2 photons. This is a relatively clean signature. You can also look into Higgs particles decays in other more complex topologies, and that's what we are looking at now. So that there are applications in this direction. Yes.
Okay, cool. There was an early question in the chat asking why you had no photo of John Ellis's desk as part of your chat. I guess it's a pretty famous thing, these photos from CERN.
Yeah.
When I was there myself, actually, I've got the book, this Inside CERN. I quite enjoyed this cover photo of Richard Kellogg. It really sums up what CERN is all about. I mean, people making coffee it's literally next to a soldering iron on his desk. It's quite an interesting place. So I know that CERN is sponsoring a summer fellowship as part of the awards here. Could you maybe tell everybody a bit about what that
yeah, so exactly. So yes, if you win the challenge, you can come and work on one of those projects this summer. So I think because of the pandemic situation, you'll have the choice of coming this year for a remote project. So unfortunately, you will not be able to be on site. We hope that next year it will be different. So you'll be able to choose whether to work remotely with us this summer for a couple of months, or wait next year and maybe have the chance to come to CERN, participate in the Summer Institute project.
Okay, what kind of projects have you run in the past, or were you planning to run?
Well, anything you saw here this is kind of a shopping list. You'll most
Okay.
likely come and work with me. I'm sorry. Um, no, but we are designing different, as I said, those are examples. We are designing really, we are trying to survey the different steps of data analysis, data processing in order to see where indeed quantum could work. A nice project is about anomaly detection, for example.
Hmm.
This part. So.
Okay. And it's also a really lovely area. Are you actually living in Geneva, or are you on the French side?
Oh, I'm on the French side. I'm yes, on the mountains. I'm on the
In the
cows,
mountains.
villages.
Which one? I lived in Saint-Genis when I was there.
Oh, I'm in Crozet. You know the one with the
Crozet.
yes, it's
Yes, that's
right
right
on.
up in the mountains. Yeah, that's a great little one. Yeah,
Yeah, yeah.
I really liked it. I was in a small three-story apartment building, which is the tallest one around, and our balcony faced the Alps, so I could see Geneva, I could see the Mont Blanc from my balcony. It was definitely one of the best views I think I've ever had in my life of anywhere that I lived and worked. It's such a wonderful place. So I understand that you're big into mountain biking.
Oh,
Uh,
yes.
but living right next to the Alps, your favorite mountain biking experience is not in the Alps, it's actually in the desert.
It is, but that's the point, right? I can go to the Alps when I want. I mean, even here, I get out my home, I'm on the Jura, I can go and ride. But yes, my best experience was in the Mohave Desert.
Wow.
Those of you who are into biking might know the Slick Rock Trail. It's a great place.
Wow. Okay. I don't know too much about what's so interesting about the
It's
Slick
a
Rock Trail.
special kind of it's well rock. It's all about the rocks, the way they are in that area. So that there is a specific trail that is famous, but the whole area in Moab has plenty of those situations. So the name comes from the fact that the rocks, the tires of your bike get really attached. They stick to the rock, so you're able to climb and go down very steep places.
Ah,
Yeah, so it's really cool. It's really cool.
okay. Wow. And you made a trip just to go there, or you happened to
I
be
did,
there?
yes, I did. No, I was in Denver. So I was in Denver for a conference, and I just had to fly across the Rocky Mountains. Yeah, so I was there. It was actually it was end of November. It was snowing in Denver. It was really bad luck, I would say. I went to Moab and it was raining. I mean, who lives from Geneva goes to the desert and finds rain? I mean, but I still managed to go. I managed to go and I didn't crash on the trail. I was very happy.
Wow, that's awesome. That's fantastic. I think quite a few of our speakers are actually into mountain biking, and it's interesting. I don't know if there's anything interesting there going on, or just coincidence. We'll have to do some investigation and find out about that.
You know,
So I had another question for you. So as I mentioned at the start, you have been a part of some amazing experiments, and one of them, the ice cube experiment, that's actually
Mhm.
stationed at the South Pole. So did you ever get a chance to go down to the South Pole and visit the facilities there?
No, unfortunately not, because I joined the experiment, the collaboration when the building, everything of the detector had already been completed, so there was no real reason to go. I mean, you could go for like 6 months shift, but that was really not my thing. Too
Six
long.
months shift? Wow.
Yes, no, that I couldn't do that. But so yeah, you couldn't go just for a little while. I mean, the trip there is very, very. You need to go through New Zealand, you need to get to Antarctica, some American based, and then they fly you to the lab. It takes days just to go.
Wow.
They
So for those that don't know, why build detectors at the South Pole? That seems like a lot of work.
Yeah, it's a beautiful detector. It's targeted to neutrino physics. So what the idea there is that you can use the pure ice in Antarctica as your your sensitive material. So the neutrinos are very elusive particles. They're very difficult to detect. So you need big, huge volumes. Ice cube is like a cubic kilometer detector, so it's a huge volume, and it's all built in the ice, inside the yeah, how you say, in the ice. In Antarctica, you put your sensors in there, and whenever and neutrino interacts with ice, then you have your photomultipliers your scintillators and photomultipliers that collect the light, and you can read it out and then make all this kind of analysis that I showed you.
Wow, it took a lot of creativity to come up with that idea for an experiment.
Well, the other option is there have been a lot of experiments under the sea. So we had one in the Mediterranean Sea just before IceCube was built. It was the same principle, just you'd use seawater instead of ice.
Oh, very interesting. Very interesting. It's experimental experimental physics. So we got a little bit of time left. I wanna play a little game that we've been playing with our guests here. It's called Real or Imaginary, and the way that this works is we've got some real quantum computing terms and some imaginary terms. They're not imaginary, they're real terms. They're just not real quantum computing terms, but they might be. So the idea is I'm gonna throw some terms at you and you have to guess, is it a real quantum computing term or imaginary quantum computing term?
Okay.
That part? Okay. Ready? Okay. Q-twist.
Q-twist? No, I think it's imaginary.
You are right, it is imaginary. So it is actually a home healthcare item for removing earwax.
Okay, good. I'm very bad at games. I'm happy I got one right. That's good.
Okay. Next, we have QuantumScape.
Quantum? Skip?
QuantumScape.
QuantumScape. Oh, this is, I don't know. I don't know. It doesn't feel, I would say it's still imaginary.
You say imaginary? Chat, what do you think? Give you a second to answer there in the chat. They're not sure either. It is. Oh, we got real. We think that it's real. It is actually imaginary. QuantumScape is. Let's see, I've lost it now. But okay, it's an American company specializing in lithium-ion batteries for electric cars. Not real. Okay. Next, already, quantum bomb detector.
Quantum bomb detector? No, this is imaginary. Come on.
Chat, what do you think? Quantum bomb detector. Real or imaginary? It's actually real. Quantum bomb detector. Also known as the Elitzur-Vaidman bomb tester. It's a thought experiment showing how to detect functional bombs without having to detonate them. Schrödinger cat style, right?
Okay.
So it's a thought experiment, quantum bomb detector. That's a real one. Okay, let's see one. Let's do one more here. Okay. Let's see. Let's pick a good one. Let's get a good one. Okay, let's go with quantum analytic descent.
Analytic descent. Quantum analytic? No, I don't like quantum and analytic descent together. No.
Okay, yes, the chat also thinks that's imaginary, but it is real. Quantum analytic descent is actually the title of a paper, and it's by QHack speaker Balint Coxor, who's coming up later in this session.
I need to read this paper now.
You've got some homework. You're going to have to go away and read the paper, Quantum Analytic Descent. Some homework as well for the chat. Check out that paper. You've got until, when's he coming up? 11 o'clock. Balint is going to be here with us.
2 hours.
Yes.
Okay. I'll read that.
Awesome. Okay. Well, thank you so much, Sofia. It's been wonderful having you. Really enjoyed the talk. And thanks everybody in the chat. We're going to take a quick break and we're going to be back at 9 o'clock with Vishal, our next speaker. Thanks a lot.